This is Daniel Coosbury, and we are starting to shift gears in our study away from looking at data for a while and looking towards probability. So in order to develop some of the statistical methods we're going to need in the future and apply them to data, we need some probability background. And so this video is going to focus on some really basic introductory ideas in probability. Now you have to mind me, I'm getting over some kind of an illness and I don't have much of a voice. So if you need to turn the volume up to hear what I'm saying, do it. Sorry if I cough or something or other, but I'm going to try to get through this one. I think I can do it. So let's look at probability. A probability experiment is one in which we do not know what an individual outcome will be, but we do know how a long series of repetitions will come out. Now that may be confusing, but let me give you an example. Imagine you're flipping a fair coin and you want to know the probability that lands on heads. Well, before you flip the coin, you have no idea whether it's going to be a heads or a tails. But we do have some kind of an idea that in the long run, like if the coin's really fair, about half the time it's going to land on heads and about half the time it's going to land on tails. Like we just know that because we've heard it and we just, that we understand that's how it works. If it's truly fair and balanced, it's going to be about a 50-50 chance you get heads or tails. So that's what we mean by after a long series. Imagine doing it 1,000 times. Then you'd expect roughly half of them to be heads, half of them to be tails. But the thing that makes it probability is that we don't actually know what any single one's going to be. So the probability of an event is the proportion of times that the event occurs in the long run. So let me go ahead and show you some probability notation. So the probability that it lands on heads, we can be a little lazy and use some words now when we start talking about probability. So I like to use the P. This is a pretty common way to talk about probability. Use a capital P and some parentheses to talk about the probability. So this is the probability that we get heads is going to be equal to 1/2. Oftentimes we write in decimal form, so you could write it as 0.5. Another way to say this that's pretty common, we do coin flips a lot when we talk about probability, is you could just put an H there for heads, a T for tails, and stuff like that. But I'll show you some more notation in a little while. But that's an example of a probability experiment. We don't know what the outcome is going to be, but we know the long run. We can talk about numbers and probabilities and things. The collection of all possible outcomes of a probability experiment is called a sample space. So we're going to look at the sample space for a few different things. So when we talk about sample spaces, we're thinking all the possible outcomes, not just one, but all of them. So if we're talking about a coin toss, the sample space, which I'm going to denote with a big curly brace and start listing things with commas. If I toss a coin, what are the things that can happen? Well, it can land on heads or it can land on tails. Can anything else happen? Well, it can stand on its side, but in reality, it's not really going to stand on its side. That almost never happens. We're not going to consider that an outcome. There's two outcomes when you flip a coin, heads or tails. So usually you list your sample space in curly braces and you list all your outcomes with a comma. So let's see, if I'm going to roll a 6-sided die, let's assume this is 6-sided. The things that I can get when I roll it are a 1, a 2, a 3, a 4, a 5, and a 6. That's another example of a sample space. So we're talking about all the possible outcomes. Another one is going to be the selection. If you randomly select a student from a list of 500 at a college, the sample space is going to be each of the 500 students at the college. So if you wanted to list them out, you might just list out all their names, or if they had ID numbers, list out the 500 ID numbers. But this is the idea of the sample spaces. We're talking about each one of them. So that's all the possible outcomes. Now let's talk about an event. In probability, an event refers to a specific possible outcome of a probability experiment. So this is different than a sample space, which refers to all the outcomes. An event is going to be a specific outcome. Okay, so let's see if we can identify a few events. First, imagine we're rolling a fair 6-sided die. This is to distinguish between the sample space and the event. We just did this one on the last slide. The sample space for a 6-sided die is going to be the numbers 1 through 6. Let's describe the event that you roll an even number. What that means is, what are the possible outcomes that I can get that would be even numbers? And they've got to come from here. This is all the possible outcomes. the event that I roll an even number is going to be the event that I roll a 2, or the event that I roll a 4, or the event that I roll a 6. So the word event, it's kind of, the definition may seem kind of vague. It just refers to a kind of outcome. And that could be a specific outcome, like I roll a 2. That could be an event. It could also be a more broad outcome, like an even number, which could be any of these things. So it doesn't have to just be a collection of things. It could just be one thing. That could be an event. But the event I'm referring to and specifically is the event that I roll an even number. All right, let's describe the event that I roll a number less than 3. So what are the outcomes I could roll that would be numbers less than 3? Well, they got to come from here, and there's only 2 numbers less than 3. So that would be if I roll a 1 or a 2. So I know this is kind of rudimentary, but this is supposed to introduce you to some terms you've probably never seen before, like what we mean by event, specific outcome, and it's usually described when we talk about it, whereas the sample space refers to all of the outcomes, all in a big group. Okay, so those are terms that need to be kept straight. Let's look at some probability rules. Pardon the math notation, but this is very, very, very precise, and it'll help you do some probability stuff right. Suppose we have n outcomes. We use n to refer to the sample size all the time. Sometimes it's referred to the size of the sample space as well. Suppose we have n outcomes in a sample space named O1 to On, so there's n of these, where OI represents the ith outcome. So if you're looking for the 7th one, it would be O7. The probability associated with any outcome must be between 0 and 1. So what that means, if I'm finding the probability of any outcome, it's got to be bigger than or equal to 0 and less than or equal to 1. So what that really means is, well, there are these boundaries that mark off how we talk about probability. If the probability that OI equals 0, which it is possible, there's an equal sign there, this is called an impossible event. So if the probability that something happens is exactly 0, it's impossible. It can't happen. The probability that OI is equal to 1, if it's exactly 1, this is what's called a certain event. Something we know is going to happen. Like without a shadow of a doubt, like it's definitely going to happen. The probability is going to be 1. Now, anytime you're doing things, most of the time probabilities end up being between 0 and 1. So they end up being decimals between 0 and 1. But the point is, if you do any sort of probability calculations and you end up with the number 5, it's bigger than 1, you've done something wrong. The probabilities have to be decimals between 0 and 1, or they could be 0 or 1. And these are the interpretations if you get 0 or 1. The other thing is that these are all your events in your sample space. Then the sum of all the possible outcomes must equal 1. And this is just kind of what it looks like. So if you have all the possible outcomes, they must equal 1. So think about probabilities being like a percent chance. If this has some percent and this has some percent, let me give you an example. Let me put numbers on these. Let's just say this is like a 10% chance this happens, and there's a 40% chance this happens, and there's a 50% chance this happens. And these are the only 3 things. Then they have to add up to equal 100%. And we understand that. Like we understand there's a 100% chance that something happens. One of these things. But there's only a 10% chance this one does, and so on and so on. So all the probabilities have to equal 1. If a sample space has n equally likely outcomes, and an event A has k outcomes, then the probability that A happens is equal to the number of outcomes in A over the number of outcomes in the sample space. So we looked at how to find events, how to write them with that die roll example. And how many outcomes we saw, for instance, with the even number, there were 3 outcomes, a 2, a 4, and a 6. So that's kind of what this would refer to. How many outcomes would make A true? Well, if we're rolling an even number, I want the outcome 2, 4, or 6. That's 3 different numbers. This would be 3, the number of outcomes. And so if we want to find the probability A occurs, it's going to be the number of ways A can occur, which is this thing, over the total number of outcomes, which is the size of the sample space, which is n. And this is kind of intuitive. It's an equation that you maybe haven't seen, but it's how we tend to think about probability anyway. Let me show you an example. In this cash lottery, a winning number between 0 with 4 digits and 9999 is chosen at random, with all the possible numbers being equally likely. So there's, every single number has the same chance of being picked. What's the probability that all 4 digits are the same? So we're going to call this A and try to find the probability that A happens. And I'm going to start by, I need to find out how many different ways can A happen. So I'm going to start by writing down all the different outcomes that are included in A. So a good question is, of all these numbers between 0, 0, 0, 0, and 9, 9, 9, 9, how many of these numbers, or which of these numbers have the same digit all the way through? I'll get us started. So for instance, 0, 0, 0, 0, same digit. All 4 digits are the same. The next one that's like this is probably 1, 1, 1, 1. And there's 2, 2, 2, 2. You see where I'm going? So I can list all the possible outcomes that would make A true. It may be tedious, but I'm going to list them anyway. One more. 9, 9, 9, 9, and I think that's it. Now, why did I list them all? Because I need to know the number of ways that A can happen, which is this K number right here. How many ways can A happen? Well, A can happen if I get this number, or that number, or that number, or that number, or that number, and so on. So I'm going to count up the total number of things in A, and that's going to be K. And then the total number of numbers is going to be N. So the total number of things in A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 things. So the probability that A happens is going to be 10 over. And then I need my number of outcomes in the sample space, which is going to be any number between 0 and 9999. Now let me point out that the numbers, if I start counting at 1, oops, hold on, something bad happened. If I started counting from 1 to 9999, that would be 9,999 numbers. Once you add 0, that bumps you up to 10,000. So my actual number is 10,000 because I'm including 0 here. 1 to 9999 is only this number. But if I add 0, then I end up with 10,000 different options. And so when I do that, the probability that A occurs is 10 divided by 10,000, or 0.000, no, 001. That seems right. So I've got yeah, that's my probability that I draw a number, the lottery tickets drawn that has the same digit 4 times. So I guess the takeaway from this is when you're looking for the probability of an event A, you got to count the number of outcomes, which might start by listing all the outcomes and then counting them. There might be better ways to count the number of outcomes, but this is a good way. Another way to do probability is by taking a pretty large random sample and using the sample to compute probability. So like when we're doing coin flips and die rolls or drawing a number at random, we can intuitively talk about probabilities because they just work all the time like that. But when we're talking about things that aren't well known, like things having to do with people or basically everything else that aren't cards and whatnot, we need another way to talk about probability. And so taking sample data is a way to do that. For instance, there's 10,000 families in a certain town categorized as follows. They either own a house, own a condo, rent a house, or rent an apartment. And we want to find probabilities that people in this town fall into these categories. And the only way to do that really is to take a random sample of this town first and then talk about probabilities. So we're going to use this sample to compute probabilities. So let's start with a few examples. What's the probability that we sample a family who owns a house? So I'm going to call this event A, that we pull a family randomly and they own a house. Well, the probability that someone owns a house is going to be found by taking this number. These are all the people that own a house in our sample, and dividing by the total number, the total sample size. So I'm going to use the formula here, just like on the last slide, where the K is going to now refer to the number of people in this category, or the number of people that would make A true. That's 4, 7, 5, 3. And N is going to refer to the sample size, which is this 10,000 right here. So this is N. So this basically works like in the last problem, Whereas in this case, K is a lot easier to count because the number of people that make A true is just right here on the table. So I can just stick it up here. And the sample size is down there. And then when I do the division, I get 0.4753. Dividing by 10,000 is easy. Just move the decimal 4 places. But that's how you do probabilities with sample data. Now let's look at a little more challenging problem. What's the probability that the sampled family rents? So now this is going to be event B, that we get a sample family that rents. Okay, well, look in my data, I have 2 different categories that rent. I have the rent a house, and I have the folks that rent an apartment. Now, this doesn't specify house or apartment. This just includes everybody who rents. So I'm going to have to count both of these in my event B. When I'm trying to find K, I'm going to have to find both of these. And then my sample size is still going to be 10,000. So what this means is I'm going to add these 2 numbers together in the numerator. So the number of people who make B true is 912 plus 2,857 over 10,000. So I had to do a little bit of finagling with my numbers, but I haven't broken any rules. I'm just getting all the renters together in one category. In fact, I could just cross out this category and make a new category for renters. And that category would have 3,769 people in it over 10,000, which gives me a probability of 0.3769. So this is the probability that you sample a family and they rent, which would mean they're in either of these boats. So that's kind of nice. So finding probabilities with sample data is really not too bad because this K number is easier to find. We didn't have to list out all the possible things. We had the number right here. The K number here was in both of these categories. We just added them together. So that was really nice. Okay, there's a third way to do probability, and it relies on something called the law of large numbers. The law of large numbers says that as a probability experiment is repeated over and over again, the proportion of times that a given event occurs will approach its probability. So I kind of talked about this when we were doing the coin flip thing. We know that we can flip a coin. We don't really know where it's going to land, but we know that in the long run, about half the time it's going to land on heads and half the time it's going to land on tails. This graph is just supposed to represent that. So if you flip a coin over and over again, the first time you get heads, the proportion of times you land on heads is 1. Maybe the next time you get tails and it's like 50-50 again. Maybe the next time you get tails and it's kind of less than 50%. But the more you toss it over and over again, the more the proportion of heads is going to get close to 1/2. So this red line represents 1/2. So eventually, if you do it long enough, the law of large numbers says that the proportion of time of outcomes that are your desired one is going to be equal to the probability that it occurs. So we're going to use the law of large numbers to do what's called the empirical method to find probabilities. The empirical method consists of repeating an experiment a large number of times and using the proportion of times an outcome occurs to approximate the probability of the outcome. So in other words, get an extremely large sample, basically, and we're going to use that to approximate probability. So if we repeat something over and over and over again, we get a huge sample, then according to the law of large numbers, then we should have enough data to compute the probabilities. And just assume the probability is the proportion, or it's approximately the same thing. So let me show you an example of this. In recent years, there were this many boys and this many girls born in the U.S., and we want to approximate the probability that a new baby is a boy. So there's a new baby about to be born. We want to find the probability it's a boy. So think of this as a repeated experiment. We repeated an experiment almost 4 million times, and a little over 2 million times they were boys, a little less than 2 million times they were girls. So we want to find the probability that we get a boy, which is the probability, which is going to be equal to the number of boys that we have over the total sample size, which unfortunately we're not told the sample size, but we can find the sample size because these are the 2 outcomes. So together they equal our sample size. If you add them up, you get n. This is my plus sign, the plus sign. Add them up, you get n. So I'm going to do this plus that in the denominator. Now be careful adding things when you're doing fractions in the denominator, or when you're doing fractions in the calculator, because bad things tend to happen. Let me show you how I like to do this math in the calculator. Whenever you're doing division and you're adding things and doing division, your calculator gets mad at you if you write things in the wrong order, which is why whenever I do it, you got to put things in the parentheses in the numerator and the denominator before you do the division. It does order of operations first. So if you do this divided by that plus that, it's going to do division first, and you don't want it to divide first. You want to add these things first. So put the parentheses around here and then do the division last. So I'm going to do this in the calculator. I'm going to do 2, 0, 4. Oh, that's not a 4. 4, 6, 9, 3, 5. Divided by, so that's the numerator, and I got to put the whole denominator in the fraction. So I'm going to open my parentheses here and then do the same thing. Plus that number, 1, 9, 5, 2, 4, 5, 1, and then close parentheses. So now you see it's going to add the stuff in the denominator before it ever does the division. And then when you finally do that, you get 0.5118 as your answer. And it's pretty customary to round probabilities to 4 decimal places. That's what I like to do. So 0.5118 is the chance that the next baby born is a boy. A little bit over 50%, not that much over 50%. Not enough that I really care to say boys are more common than girls, but anyway, it ends up being close to 50-50 based on this data. So that's an example of using a huge sample, a repeated experiment to find those long-run probabilities. This is definitely a huge sample. So that's called the empirical method. All right, the very last thing I'll show you in this video, it's really quick. We're going to need this concept later. So different people who do probability and do statistics do them different ways and have different terms for things. And but before we start talking about statistical methods, we need to define a concept of unusual. So how small should a probability be before we call it strange or unusual or unlikely? And an incredibly common cutoff is going to be less than 0.05. So not everybody agrees this is unusual, but for the purpose of this class, we're going to say an event is unusual if the probability that it happens is less than 0.05. And that's going to come up a lot later when we do these. Other people may think that's not unusual. Other people may say it's really unusual. You know, whatever, we disagree. But we'll agree in this class that less than 0.05 is going to be unusual. So in a college of students, of 5,000 students, 125 are business majors. We're going to select the student at random, and it turns out to be a business major. Is this unusual? Well, let's find out. Let's find out the probability that we select a business major, which is going to be the number of business majors over the whole number of students, which is going to be 125 divided by 5,000, which is 0.025. And this is less than 0.05. So this is kind of the takeaway. The question is it unusual? I found the probability, it's less than 0.05, so I'm going to say yes. It's going to be unusual. And that's all you really have to do to answer questions like that. Again, that's going to come into play later, especially when we start looking at statistical methods. We're going to start looking at data to suggest, is it unusual that this happens based on the data? And what can we say about it? But anyway, those are some very basic probability properties. You're going to want to watch the next videos in order to learn how to do some more complicated problems. But I hope this one is enough to get you started doing some probability.